Hey everybody, welcome. This time I'm going to follow up last video about series equivalent resistance with this video on parallel equivalent resistance. So I'm going to go ahead and draw out an example circuit and set things up kind of like I did last time. Okay, so this is very similar to the circuit I drew last time. The exception being that now I have three resistances in parallel rather than in series. And I've posed the problem or the question in kind of the same way, where I have a voltage source with a resultant current that's drawn from it due to the load presented by these resistances. And I'm sort of drawing this dotted line to separate the source from the passive or absorptive components. And the question being, is there an equivalent resistance that we can use, or a single resistor, to model this entire network of parallel resistances? The answer is yes, just like the series case. And so let's jump right into that. The first thing that you probably want to realize in this case is that we have a parallel circuit, and I've talked about this many times in previous videos. But let's start by analyzing the current that flows through these resistors. So we have this given current I, and I think the most natural thing to do in this case is to apply a KCL. So if you notice, all this current must flow through all the resistors. So we can go ahead and label that I1, I2, and I3. So each of these resistors has a current, and it should be very clear by now, the basic principle of KCL or Kirchhoff's current law. We know immediately that the total current flowing from the source has to equal the sums, or the sum of all the currents in the circuit or in these resistors. So this is just a KCL at this node here. And we also know that each of these resistors will have some resultant voltage across it. And I'll go ahead and label that now. So V1, V2, and V3. Excellent. But then this is where we apply our knowledge of parallel circuits. And something that I've discussed prior is that we already know each of these voltages V. In fact, because this is a parallel circuit, here, therefore we actually know already that all of these voltages are equal. V1 equals V2 equals V3. So all the elements in a parallel circuit have the same voltage across them, and this is all equal to V, which is the source voltage here. So at this point, with this knowledge in mind, now let's approach this KCL. So we're looking for an equivalent resistance here, so it's probably in our best interest to try and express the relationships we know in terms of these resistances, because I want an equivalent resistance that's a function of all these parallel resistances. So I'm going to go ahead and apply Ohm's law to my KCL here, and that's going to allow me to transform this into a function of voltages and currents. So we know that I1 via Ohm's law is just the ratio of V1 to R1, and if we apply that for each element in the circuit, we're going to be left with this equation where the total current leaving the source is equal to the sum of the volt-ohm ratios at each component. So V1 over R1 plus V2 over R2 plus V3 over R3, where these are each a current. These each have units of amps. But we also just realized that all of these voltages are equal, which allows us to express this in this way: V over R1 plus V over R2 plus V over R3. And we can factor that. V times 1 over R1 plus 1 over R2 plus 1 over R3. Okay, now we want this to be, we're looking for a resistance here. And ohms has the units of volts to amps. It's, resistance is a volt-amp ratio. So let me go ahead and relate that. So I have a voltage here, and I started with this current. So with a little bit of algebra, I'm left with the expression V over I equals 1 over R1 plus 1 over R2 plus 1 over R3. And this whole thing has units of resistance. Remember, volts to amps. That's a resistance. This is a volt-amp ratio. And think about it this way. The denominator has units of inverse ohms, but then we're taking inverse of inverse. So really, the units of this entire expression is just ohms. And so we'll probably write this as R eq, or R equivalent. And in this case, if you allow me to redraw our model circuit, we have now formulated or identified some value for a resistance that could be substituted in this case and yield identical behavior or performance in this circuit. So the point I'm trying to make here is I could have a single resistor with this equivalent resistance on the right side of this dotted line, and you would never know the difference. If this was in a box and you couldn't see what was inside, the same current would flow for the same voltage. And like I mentioned in the previous video, a lot of times in electrical engineering, this just makes our analysis easier, and it makes things easier to talk about. And so like I talked about in the case of the series resistance, this isn't specific to 3 resistors. I mean, it could be 2, it could have been 4, or any number. This pattern will persist. So if there wasn't a third resistor here, our equation would just be this. Okay, we just have one less term. And if there was 4, you would continue adding 1 over R4 plus 1 over R5 plus 1 over R6. And so this is also a general case derivation for any number of parallel elements. And with that, I think I'm going to close up this video. This is another short and sweet one. And we'll get into, I'm not exactly sure what I'm going to do in the next video, but I hope it comes soon. So I guess to close that out, yeah, let me know if there's anything you'd like to see or anything I can help with. And I really hope this was helpful. Thanks for watching, and have a great day.